Greetings, welcome to the 18th lesson in a series of lessons on basics of power systems engineering. This presentation covers application of voltage divider and current divider equations to AC impedance circuits. This will be done through the use of two example circuits. I will then propose another impedance circuit with two AC voltage sources in it and apply Thevenin's theorem to find the current through one of the impedance elements in that circuit. And finally, I'll work the same circuit, this time using the superposition principle to find the current in the same impedance. Of the circuit laws and theorems, I will not be reviewing Ohm's law or Kirchhoff's laws for AC circuits because they have been covered in the earlier lessons for resistive circuits, although I will be naturally using those theorems and laws in the process of AC circuit analysis. I will, however, cover application of voltage and current dividers to AC circuits, as mentioned earlier, as well as Thevenin's theorem and superposition principle in this lesson. I will cover loop and node analysis of AC circuits in future lectures. Since concepts have already been covered for DC resistive networks, I will pick up the pace here and will be skipping some of the intermediate steps of calculations. It is a good idea, however, especially for those who need a more thorough review, to do these intermediate steps independently and check out their results against what I show on these pages. Let's start with the concept of a voltage divider. A voltage that appears across a series combination of two impedances, such as this one, will be distributed across each impedance in proportion to that impedance's value relative to the sum of the two impedances. In equation form, for each of the two voltages V1 and V2, we'll have these equations. V1 equals V sub S times Z1 over the sum of the two impedances. And V2 is Vs times Z2 over the sum of the two impedances. Proof of these equations is easy to come by, although I will not go over it here, but here's an outline of how to prove it. Take a current I going through this circuit. You can find this current in terms of Vs and Z1 and Z2 by using the Ohm's law, Vs over Z1 plus Z2. Once that is done, multiply this current by each impedance to find the voltage drop across that impedance, which will result in these two equations. To apply these two equations to this circuit, we substitute for the source voltage of 220 volts and Z1 and Z2, the values of which are given. The result is 220 times 2 plus J4, which is Z1, over the sum to give you V1. And for V2, you have 220 times Z2 from here over the sum of the two impedances. Crunching the complex numbers here, we'll have these values for the answer in volts. To check on the results, I'll add V1 and V2, which should give me back the Vs, the 220 with 0, according to the KVL. Here are the two voltages, V1 and V2 added, and if you do the addition, you should get 220 with 0 volts. Let's now move on to the construct of current dividers. The idea here is that if a current is branched off to two impedances in parallel, the current flow in each impedance would be in proportion that is inverse to the value of that impedance. Here current I is coming in, is getting subdivided into I1 and I2, going through two parallel branches, Z1 and Z2. I1 and I2 are calculated based on this formula, these two formulas here. I1 equals I times Z2 over the sum, and I2 equals I times Z1 over the sum. Here we are given the current I, the total current coming in, 15 amperes with 0 degrees, and both of the impedances are given, of course. And substituting those values into our equations will give us 15 times Z2 over the sum of the two for I1, and 15 times Z1 over the sum gives us I2. The answers are these values here, 13.13 amps with negative 1.835 amps for I1, and 1.926 amps with 12.61 degree phase angle for I2. Again, to check out the result, I'll add the two currents I1 and I2, and based on KCL, they should add up to the value of I. I comes to this node, and two currents go away from this node, so the two currents going away should add up to the one that's coming in, and they do add up. I1 and I2 add up to 15 amps. Next, I'll work out an example of the application of Thevenin's theorem. Before doing that, though, I would like to take a short break to introduce myself. My name is Fuad Alvandi. I'm a PE in Electrical Power Engineering. This is the 18th lesson in a series of lessons on basics of electrical power engineering that I have published on the YouTube. You find my name, web address, and email address on this page. I invite you to visit my website for comprehensive modules on power systems engineering topics. The website address is own-your-destiny.mylearnworlds.com. I will now continue this lesson with the application of Thevenin's theorem to a sample impedance circuit. In the circuit on this page, let's assume that we are interested in finding the current that flows in the center impedance. Using Thevenin's theorem, we're looking for I. The voltage sources are given, and the three impedances. The first thing we need to do is to remove the center impedance, as I've done on this page here. Once the impedance is removed, I'll find the Thevenin equivalent circuit of the remaining circuit viewed from the port AB. Finding the Thevenin equivalent circuit takes place in two steps. First, we need to find the open circuit voltage between points A and B, in other words, VAB. To do this, I'll assume a current of I for the circuit and write the KVL for it. Assuming current of I, lowercase I here, going through the circuit, I'll take the KVL in this direction. Starting from point B, there's a voltage rise of 20 volts. I wrote that on the left-hand side. And there are three voltage drops, which will add up on the right-hand side. The first one is I times this impedance. That's the first term. The next voltage drop is I times this impedance. Again, plus minus. And this is that term, the second term. And the last voltage drop is 10 volts with 2.5 degrees. And that's this term. The three of them added together should add up to the size of the voltage rise. We have an equation in I which can be easily solved to give I, and I is calculated to be 1.718 amps with negative 33.46. The goal was not just to find I will be used to allow us to calculate VAB. And VAB will be then 20 minus the product of I and this impedance. I is found numerically, we have it. We multiply it by 2 plus J4 and subtract that voltage drop from the 20 volts to get the VAB. And that's shown here. VAB equals 20 minus product of the current I times this impedance. I'll make a note of this voltage and move on to the next step. Here is that voltage that was just found. This next step is to zero out the voltage sources and find the equivalent impedance seen from port AB. The equivalent impedance is simply the parallel combination of these two impedances. So ZAB is 2 plus J4 in parallel with 3 minus J4. And that gives us 2.425 ohms with 14.04 degrees. I'll make a note of this impedance as well. Here they are, VAB and ZAB are calculated. We'll rename VAB to VTH, TH for Thevenin, and ZAB to ZTH again for Thevenin. This one is the Thevenin equivalent voltage source, and this one is called Thevenin equivalent impedance. We'll put these two in series, a voltage source of this magnitude in series with an impedance of this size to get the Thevenin's equivalent circuit shown on this page. Here it is, the voltage source with the Thevenin voltage and the Thevenin impedance calculated earlier. Having formed this Thevenin equivalent circuit, I will now replace the impedance that was originally removed. This one goes back between points A and B. And using Ohm's law, by dividing this voltage over the sum of these two impedances, we can find the current I that we were looking for. And here it is. I equals the voltage over sum of the two impedances. And I comes to 1.025 with amps with negative 40.4 degrees of phase angle. I'll now go back and redo the same example, this time using the superposition principle. To apply the superposition principle, we zero out all but one power source and find the required voltage or current that we're looking for due to that one source that is left in the circuit. This is done in turn for each of the sources in the circuit, after which the results are added together to find the answer with all the sources on, or in other words, to find the result for the original circuit. Voltage sources are zeroed out when they are replaced with a short circuit, and current sources are zeroed out when they are replaced with an open circuit. For this example, again, we're asked to find the current through the center impedance. I'll first zero out the voltage source on the right, this one, and find the current through the center impedance due to the 20 volt source alone. And then restore the source on the right and zero out the 20 volt source this time. and then find the current through the center impedance due to the 10 ohm, due to the 10 volt source alone. Once those two currents have been found, I'll simply add them together to find the answer. Here is the circuit with only the 20 volt source left active. I'll first find the I current shown here by dividing the 20 volts by the equivalent impedance seen by that source, which would be these three. The equivalent impedance is going to be the sum of this impedance with the parallel combination of these two impedances seen in the denominator here, 2 plus J4, added to the parallel combination of 3 minus J and 10 plus J5. In the denominator, the numerator will have the voltage source, 20 volts. And the answer comes to 3.441 with amps with negative 38.2. Now to find I1, we need to take this current that was just found and do a current division at this node to find the current through the center source, center impedance, excuse me. Here is the current divider applied to this example. The current that was just found, I, times, because we need the current in this branch, we put the other impedance in the numerator, 3 minus J, over the sum of the two impedances, this one and this one, comes to this value for I1. Now we'll zero out the 20 volt source and find the current due to the 10 volt source. And here's that circuit in the bottom. First, let's find I prime, again by dividing the voltage here by the equivalent of the three impedances here. And here's that equation. I prime equals the voltage, 10 with 2.5 degrees, over the sum of 3 minus J added to the 3 minus J added to the parallel combination of these other two impedances. And the answer is 1.897 amperes with negative 15.93 degrees. So we have the I1 from this source alone and I2 from this source alone. Superposition principle tells us that the overall current would simply be sum of these two. So I will add I1 and I2 to get the answer. Answer I comes to 1.024 with negative 40.4 degrees in amperes. This result should match the value that was found for the current using Thevenin's theorem a few slides back. We have reached the end of lesson 18. If you enjoy watching my channel, please click on the subscribe button and the notification bell. If you're looking for a resource to review topics in preparation to take the PE exam in electrical power engineering, you may find the modules on my website to be helpful. Here is the website address. Thanks for watching this video, and I hope to see you soon in another one of my presentations.